Roses are red and violets are blue. Colors intrigue artists and physics types too. My Lil and I are certainly intrigued by our colorful pet conure, Sneezely. And here's physics teacher and artist Jeff Weatherhold, who obviously is passionate about color. To physics educators like Jeff, the colors of objects go beyond the light they emit or reflect. Color is a physiological experience and is in the eye of the beholder. So when we say that a rose is red, in a strictest sense, we mean that it appears red. Many organisms, including people with defective color vision, do not see the rose as red at all. The colors we see depend on the frequency of the light. The lowest frequency is red and the highest frequency is violet. Between them range the infinite number of hues that make up the color spectrum of the rainbow. Physics teacher Bruce Novak made up this chart to show that the colors of the rainbow, red, orange, yellow, and so forth, blend from one to the other. And he shows this blending even better with his photo of the color spectrum. These colors equally mixed together appear white. The white light from the sun is a composite of all the visible frequencies. This is easily demonstrated, as Newton did some 350 years ago, when he passed sunlight through a prism to form a rainbow-colored spectrum. This spreading of light by a prism is called dispersion. Newton went on to use a second prism to effectively undo the dispersion and recombine the spectrum to white light. Newton found fame with this discovery long before he developed his laws of motion. Note the left and right faces of the prism pair are parallel to each other, just as opposite sides of a pane of window glass are parallel. Light is displaced from its original direction, but not dispersed. Sometimes the edges of window glass are beveled to disperse light and produce a nice prism effect. The intensity of light from the sun varies with frequency, being most intense in the yellow-green part of the spectrum. Interestingly, our eyes have evolved to have maximum sensitivity in this range. That's why fire engines and tennis balls are often yellow-green. That makes them easier to see. The graphical distribution of brightness versus frequency is called the radiation curve of sunlight. Most whites produced from reflected sunlight share this frequency distribution. All the colors equally combined make white. Interestingly, the perception of white also results from the combination of only red, green, and blue light. Here the solar radiation curve is divided into three regions: low frequency red, middle frequency green, and higher frequency blue. In short, we say RGB. And how have our eyes evolved? Within our eyes are three types of cone-shaped receptors that perceive color. Want to guess what the three colors our cones are sensitive to? That's right, RGB, red, green, and blue. When all the three types of cones are stimulated equally, we see white. Project red, green, and blue lights of equal brightness on a screen. Where they all overlap, white is produced. In physics language, colored lights that overlap are said to add to each other. So we say that red, green, and blue light add to produce white light, and that any two of these colors of light add to produce another color. RGB are called the additive primary colors. Where two of the three colors overlap, another color is produced. When we overlap red and green, yellow. When we overlap green and blue, greenish blue, which we call cyan, the color of tropical seawater. When we overlap red and blue, magenta, one of the vibrant colors of bougainvillea foliage. When two colors add to produce white, they are called complementary colors. We see that red and cyan add to produce white, so red and cyan are complementary colors. Likewise for green and magenta, and for blue and yellow. The colors cyan, magenta, and yellow are called the subtractive primary colors. Why subtractive? Pigments in paints and dyes absorb, That is, subtract specific colors of light and reflect the rest. Pigments that produce the color red, for example, absorb the complementary color cyan. So something painted red absorbs mostly cyan, which is why it reflects red. In effect, science has been subtracted from white light. Something painted blue absorbs yellow, and so reflects all the colors except yellow. Take yellow away from white, and you've got blue. Subtract magenta from white light, and you've got green. Colored photographs make use of cyan, magenta, and yellow dots. When light illuminates the photo, light of some frequencies is subtracted from the light reflected. The rules of color subtraction differ from the rules of light addition. Examine any color print with a magnifying glass to see the overlapping colored dots. These show a wide range of colors. Or look at a billboard up close. Here's a photo of my grandkids, and a plate for each color of ink. In color subtraction, where color printing applies, the ink colors are not RGB, but CMY, cyan, magenta, and yellow. For a quality print, add some black. Then you have CMYK, where K stands for black. The magenta, the yellow, the cyan, combined, and then the black. All combine to produce the finished product. Yum to color printing. Our coverage of color is brief, and much more could be said. For now, I want to leave you with a question. When looking at the beautiful greenish blue of tropical waters, one particular color, more than others, is absorbed by the water. What is that color? Until next time, good energy.